All right, so let's talk about electron configuration a little bit. Okay, so when you look at your periodic table, right, you have all these different type of elements, and they're all situated in a certain type of way, in a certain type of pattern. They're in so many categories, and so forth. But you can write what we call electron configurations. How are these electrons sitting in the orbital? Okay, which when you look at your book, you can see that there's several different orbitals. One that we most often look at are S, P, D, and F. Okay, those are the main orbitals we look at. And for the context of this class, we usually even keep it more constrained just between S, P, and D. Okay. So this is how we're going to start this off. Let's start off with, for example, hydrogen. Okay, number one on the list. Okay, so let's talk about hydrogen. What do we know about hydrogen? Well, it has atomic number of 1, atomic mass of 1.008, it has a chemical symbol of H, right? And we know a few things. But what is this electron configuration? Well, we kind of do figure this out kind of like a little typewriter. We got to go left to right, backwards and forwards a little bit to figure out its configuration. So the configuration for hydrogen is 1s1. Okay. So what this is indicative of is essentially the row. Okay. So we can say this is the row that we're dealing with. All right. You can also think of this as N, or the principal quantum number, when we're thinking about this. Remember, principal quantum dealing with shells. All right. Overall, we have the orbital that it's in and the electrons. Okay. Is how we're stacking this up. If we draw our own nice little periodic table into sections, right? The way, a little crew representation, but it gets it across. We can basically break it down if we want to, or break it down to here. When we were looking at this, it's trying to figure out where it is, right? We can say essentially, this is my S, these are D's, these are P's, and these are F's. Okay. So again, whenever we look at this, these are my s orbitals, these are my d orbitals, these are my p orbitals, these are my f orbitals. If it is situated anywhere in those, that's how we name this. Okay. One exception to that is helium now, because helium is going to be essentially 1s2. Okay. So this technically resides in still the s orbitals. Now, as you may remember also, each one of these orbitals can only house so many electrons, okay? So when we're looking at this, S can house 2 electrons, all right? When we're looking at P, it can house actually 6 electrons. When we're looking at D, it can house actually 10 electrons. And when we're looking at F, it can house 14 electrons, okay? When we're looking at this over here, this has essentially basically 1 orbital, 3 orbitals, 5 orbitals, and 7 orbitals. Now what you want to keep in mind is that each orbital can only house 2 electrons, one spin up, one spin down. Okay, remember, each orbital can only house 2 electrons for a total of the number of electrons that are already presented in front of you. Okay. So when we're trying to name these things, right? If we go on, let's do lithium. Lithium is going to be 1s2, 2s2, and then I'm going to do 2s1 actually. So it's 1s2, 2s1. You kind of get through it and just it becomes pretty straightforward after a while, because what you have to do whenever you're doing electron configuration, unless you're doing a noble gas configuration, is you have to precede it with everything else. And the way you can check it is by looking at the overall superscript. Here's a 2, here is a 1. Check the atomic number. Unless it has a charge, that throws it out in that case. What you want to remember is that these here can represent overall the number of electrons. Remember, the number of electrons mimic the number of protons, okay? So due to the fact that the atomic number of lithium is 3, we know we have 3 electrons, unless it was like lithium plus, okay? So if we keep going, we'll do beryllium. That's going to be essentially 1s2, 2s2. Okay, check the numbers, atomic number, for everything lines up pretty nicely. If we keep going, we can do boron. Boron is 1s2, 2s2, right? And then we can do 2p1, okay? Remember, still can count the number of electrons, but now I'm in the p orbitals, okay? Now I'm in the p orbitals. But I think you get the gist of that. Let's say, for example, let's look at d orbitals. All right, let's look at d orbitals. Let's say vanadium, for example, vanadium. That is V. That is on the fourth row. Okay, essentially third when you're looking at the d orbitals, but in general, when you're looking at the periodic table to find it, that's how you can look for it. So V, right? The way we can do this, if we write this all out, we have 1s2, so we do vanadium. 1s2, 2s2, 2p6, 3s2, 3p6, right? Just going down the line. And then I have 4s2, and then I have 3d3. What you want to remember is that essentially the lanthanide and actinide series, right, they're not incorporated in the standard periodic table. But when you incorporate them, everything actually rises up. So it's actually 3d, not 4d3, okay? If we keep going, let's say, for example, I want to do selenium, right? Let's do Se. We can do 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and then we essentially can do 4p4. Okay, that would be selenium. All right, you want to keep that in mind. That is selenium. All right, so what do we do when we have charges? Well, that kind of changes the game just a little bit, okay? So say, for example, if I have F minus, okay, that is a charged particle. Remember, if it's an anion, we're adding electrons. If it's a cation, the cation takes away electrons. All right, so since it's F minus, which is also sometimes known as fluoride, we can say that it's essentially 1s2, 2s2, all right, and I want to go to 2p6. This is because I've added an extra electron. Fluorine in of itself is going to be 1s2, 2s2, 2p5, right? But since I've added an electron, it's going to be 2p6, and that's for the cation too. If I have a cation, let's say, for example, let's see, what's a good one? Magnesium, right? Let's do magnesium 2+. If I do magnesium 2+, it's going to be 1s2, 2s2, 2p6, right? Because I've taken 2 electrons away, and now I'm left with this configuration. The regular configuration for magnesium is 1s2, 2s2, 2p6, 3s2, okay? How do transition metals with charges behave? Well, I'm going to show you. They're a little peculiar, all right? One, first and foremost, that you want to remember is that for d orbitals, all right, if it has a charge, it wants to take from the s before it starts taking from the d orbitals. I repeat, they start taking from the s before they start taking from the d orbital. So say, for example, if I have iron 2+, okay? Iron 2+ is going to be a bit long, but it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, right? And then I have 4, what? I was going to have 4s2, right? The problem with that, if we're looking at this, remember, it takes away from the s orbital first. So it's actually going to be 3p6, and it's going to be 3D, and we count 1, 2, 3, 4, 5, 6, so it's 3D6. Okay, because it took away from the S. Now, if it was iron 3 plus, obviously it would actually be 3D5. Okay, so keep that in mind when you're doing your configurations. Now, how do I do a shorthand of iron? Let's say we just do the shorthand of iron or the noble gas configuration iron. What you want to do is you want to always pick the noble gas that precedes it. Don't be fooled by any other manipulation of it. Always choose the one that precedes it. Okay. So say for example, if I want the noble gas configuration of that same one, say for iron, I'm going to do AR. And then I'm going to do 4s2, and we'll do iron here. 4s2, 3d6. That is going to be the noble gas configuration. Now there's some other exceptions also. If I have chromium and down, and then I have copper down, what they want to make sure is they want to have half and full. So half, and we want full. That's what it strives to have. Strives to have, and full. Okay? So when we're looking at this, the normal configuration would be, if we do essentially the noble gas, or the shorthand, is going to be argon 4s2 3d4, due to the fact that it wants at least a half, is going to be 4s1 3d5. Then only for chromium down and copper down. Don't do that for anything else. So copper, same thing, is going to be essentially argon 4s2 was normally what it is, right? 3d, so we want to mark this one out, 3d 9, and in actuality it's argon 4s1 3d10. Okay, all right.